You see them on every modern PCB. Two traces running side by side, locked together, snaking across the board. USB, PCIe, HDMI, DDR, Ethernet, SATA. If a signal moves fast on a board, it almost always moves as a differential pair. But why? Why two traces instead of one? Why the matching, the spacing, the constant fuss about coupling? The answer goes back to one problem. A single trace cannot survive in a noisy world above a certain speed. So engineers built something that can. In this video, I'll explain what a differential pair actually is, why it works, and why understanding this is the entry ticket to every high-speed interface you will ever route. Here's the NVIDIA Jetson AGX Orin carrier board. Every high-speed interface on it, whether that's USB, PCIe, the camera serial links, they all run as a differential pair. Two conductors, equal in length, equal width, and they have a constant gap, and they're always together. A single-ended trace sends a signal as a voltage relative to the ground. The receiver compares the trace voltage to the ground reference and decides whether the bit is a 1 or a 0. This works fine at low speed, but it breaks down at high speed. It breaks down because ground is not perfectly quiet. Return currents flow through the ground plane. Other circuits inject noise into the same ground. Power supply ripple shifts through the ground reference. At low speeds, the signal is so much larger than the noise that the receiver still gets the right answer. But at gigabit speeds, the noise gets close to the signal level and the receiver starts making mistakes. The fix is to stop comparing the signal to the ground. You want to compare the signal to its own opposite instead. Send two copies of the signal, one that's normal and then one that's inverted, on two traces that are routed together. At the receiver, you then subtract one signal from the other. That subtraction is what makes the entire thing work. Here's what that looks like in Sigrity X Aurora's topology workbench. The transmitter sends two signals, the positive leg and the negative leg, equal in magnitude but they're opposite in polarity. They travel down the two traces of the differential pair, and at the receiver, the chip subtracts the negative leg from the positive leg. Then the signal doubles. That is the first benefit of differential pairs. The second benefit is what happens to noise. Any external noise that couples onto the pair tends to hit both traces almost equally. Electromagnetic interference from a switching regulator, crosstalk from an aggressor or a nearby layer, even a shift in the ground reference. If the noise hits both traces the same way, the subtraction at the receiver will remove it. But in this case, the noise cancels. That is common mode rejection, and it is the entire reason differential pair signaling exists. A single-ended signal carrying the same data through the same noisy environment shows the noise riding on top of that signal. The receiver sees that noise. At high speed, that noise closes the eye and the bit error rate will climb. The differential pair version cancels that noise at the receiver, as long as the noise is equally coupled. You'll get the same data rate and the same noise environment, but two different outcomes. Now let's look at the difference between a differential pair and a single-ended trace. There is a second physical effect worth knowing about, and Cadence's field solver shows it directly. On the left hand, you see a differential pair. On the right is the single-ended trace. The same plane below them, same cross-section. However, the single-ended trace pushes its electric field out in every direction, whereas the differential pair contains its field locally between the two conductors and down to the plane. You can see the field lines themselves. The differential pair forms a tight loop between the two conductors and the plane. The single-ended trace pushes fields out in every direction. The magnetic field shows the same story, but from a different angle. Currents on the two legs of a differential pair flow in opposite directions at any instant. The magnetic field wrapping around one trace points in one direction, while the field wrapping around the other differential pair trace points in the opposite direction. Outside the pair, these fields partially cancel. A single-ended trace, however, has no opposite direction partner, so its field radiates freely. This matters for two reasons. The pair emits less interference to the rest of the system, and simultaneously, the pair picks up less interference from the rest of the system. Both effects make high-speed signaling possible. So, a differential pair gives you three things that a single trace can't. You get a bigger signal at the receiver because you double it through subtraction. You get lower noise at the receiver because of the common mode noise cancellation, and less electromagnetic interference because the fields will partially cancel. That is why USB 3.2, PCIe, HDMI, DDR, and basically every high-speed interface on a modern board uses differential pairs. The voltage swing on most differential interfaces is small. A few hundred millivolts between the two legs is common in protocols like PCIe and USB 3. The exact level depends on the protocol and the generation. The receivers are designed to detect that small differential swing reliably because the common mode rejection handles the noise. Routing a differential pair means controlling several things at once. The two traces must be the same length, so the two signals arrive at the same time. The spacing between them must be controlled because that spacing sets how tightly the pair couples to itself. The trace width and the distance to the reference plane must also be controlled because together they set the differential impedance, typically 90 or 100 ohms depending on the protocol. And the return path under the pair must be continuous because the pair still needs a reference plane below it to behave correctly. A differential pair is more than two traces routed together. It's an entire system. You have two conductors, a reference plane, a transmitter that splits the signal, and a receiver that recombines it. Every constraint you set on a differential pair is there to protect one of those parts. Once you see it in that way, the rules stop feeling arbitrary and start making a lot more sense. In the next video, we route a basic differential pair in Allegro X PCB layout. See you there.